And we're going to use something called L'Hopital's rule. And that's helpful if we were trying to find the limit of something and either we got 0 over 0 whenever we were trying to plug directly in. If you remember all the way back from our first chapter, we first try to sub in directly, but we figured out sometimes that doesn't work. Because if I get 0 over 0, that's called the indeterminate form. Or if I get infinity over infinity, that's indeterminate. It means there is something there, but I can't find it unless I use another tool. And now we're ready for L'Hopital's rule. And here's what it is. It's really pretty powerful. It means if plugging in directly doesn't work because I either get 0 over 0 or infinity over infinity, then I'm going to take the derivative of the numerator and the derivative of the denominator. Now notice I'm not using the quotient rule here. I'm just going to take the derivative of the top over the derivative of the bottom, and I'm going to try to plug in directly to that. And if that gives me a value, that's going to be my limit as x approaches that number. If it gives me 0 over 0 again, I'm going to take the derivative again of the top and the derivative of the bottom until it gives me something that is no longer indeterminate. Okay? Now, let's look at a few examples here. If I try to sub in directly using as x approaches 5 on this function, okay? Let's see what happens. If I put in 5 and I cube it and I subtract 64, what do I get? Does it? Okay, 4 would make sense because I can actually plug in 5 and I'm going to get a number. So let's correct that. Let's do x approaches 4. Because if I plug in 4, how much is 4 cubed? I'm going to get 0 on top, and then if I take 4 and I square it, plus 4 times 4, and then I subtract 32, do I get 0 on bottom? Yes. I do, because that's 16 plus 16, which is 32 minus 32 gives me 0. So that's the indeterminate form. That means this is a good candidate for L'Hopital's rule. So I am going to use the limit as x approaches 4 of the derivative of the numerator over the derivative of the denominator. Okay, so differentiate x cubed minus 64 for me. What will you get?
3x squared.
I'm going to get 3x squared over what is going to be the derivative of the denominator?
8x plus 4.
Won't it be 2x plus 4?
I'm looking at something different, sorry.
That's okay. So we're going to get 2x plus 4. Now, let's see what happens if we sub in directly. If I put in 4 for x, what's in my numerator? 4 squared is 16. What's 16 times 3? 48. Over in the denominator, if I put in 4 for x, 2 times 4 is 8. And what's 8 plus 4? Can I reduce 48 divided by 12? I got an answer. Okay? And that's how you're going to get it, if you end up with that indeterminate form. Now, if I look at this next one, before I even start, if I'm trying to get my value as x approaches infinity, what happens in the numerator if I'm plugging in infinity? What's infinity to the 4th power? Still infinity, is it not? And it doesn't matter if I multiply it by something else and I add 17, am I still going to have infinity on the top? Yes. What about in the bottom? Same thing. This is infinity over infinity, which means it's a candidate for L'Hopital's rule. So let's see what happens if we take the derivative of the top over the derivative of the bottom. Now, it would take me a while to actually get rid of all those exponents. Instead, there's a way we might be able to get there a little faster. I mean, and what I'm saying is we can use L'Hopital's rule. It's just going to take us a while to get rid of all those exponents. But if you remember back in chapter 2, what was another option we could do? Is my problem that I've got this x to a power and my x is infinity. That's the issue, is it not? So I have an x to the 4th on the top and I have an x to the 5th on the bottom, okay? One thing I could do is divide everything by x to the 5th and I could work it out. But let's just see what happens if we use L'Hopital's rule, okay? I'm just mentioning there was another way to get there on this one because we could divide out by x to the 5th. But let's use L'Hopital's rule. What's going to be my derivative in the numerator? 12x to the 3rd, right? And then the derivative of 17 is 0. Over. My denominator becomes what? And if I try to sub in, am I still going to have infinity over infinity? Let's go again. All right, take the derivative of the numerator. What are you going to get? 36x squared over the denominator is 120x to the 3rd, right? Still going to get infinity over infinity. We'd have to go again. So we'd have the limit as x approaches infinity. What's my numerator now? 72x over 3 times 120 is 360 x squared. And I still have an x on top and an x on bottom. I've got infinity over infinity. We got to go one more time. What's my numerator now? 72 over, what's going to be my denominator? 720x. Now, at this point, I have 72 divided by infinity. You may have already figured out where this thing is going, but if we do L'Hopital's rule one more time, what do you get when you differentiate a constant? 0 on top over what's in the denominator. And what's 0 over anything? 0. Took us a while to get there, but it's very doable using L'Hopital's rule. So if you didn't want to divide every term by x to the 5th and apply those rules from chapter 10, then this would be the way to do it. Okay. On this one, it says explain why L'Hopital's rule does not apply to the following problem. And if the limit exists, find it. So do you think we would have an issue on this one plugging in directly? Should we always try that first? I think so. So if I plug in 2, what will I get in the numerator? 3 times 2 squared. What's 2 squared? 4 times 3 is? So what's 12 minus 7? 5 on top. Over. Plug in 2 in the denominator. What is 2 to the 3rd power? 8. And 8 times 2 is 16. What's 16 minus 13? That's going to be my limit. I could sub in directly. I don't need L'Hopital's rule. Okay? There's no reason. The only time I use it is if I had 0 over 0 or infinity over infinity. Okay? Now, this one says use L'Hopital's rule to find the following limit and then verify by using a second method. And so this is kind of where we're going to go back and review some of those things we did in chapter 10. So I want to find the limit as x approaches 3. Now, if I'm meeting L'Hopital's rule, it's because when I plug in 3, I'm going to get what over what? 0 over 0. So double check that for me. If I plug in 3 in the numerator, is that going to give me 0? Because I get 9 minus 30 plus 21, that's 0. We have a different problem here?
It's the same problem, it's the same problem, limit of 7.
I don't even have the R.
Okay, yeah, some of these, like I say, I have some notation issues whenever it prints out. So if you see that little, looks like a trademark sign with an R and a circle around it, that's actually supposed to be an arrow pointing to the right. Let me double check on this. Actually, you're right. 3 is not going. 3 worked in the numerator for giving us 0, but it won't work in the denominator. So let's fix that. You guys have x approaches 7. I don't know why this is really strange that I have the wrong numbers showing up on mine. Okay, so x squared minus 10x plus 21. Now, double check. If I plug in 7 in the numerator, does that give me 0 on top? That's 49 plus 21, that's 70, minus 10 times 7 is 70. I get 0 on top. I'm going to get 0 on bottom. So let's try L'Hopital's rule. We'll take the limit as x approaches 7. And in the numerator, when I differentiate, what do I get? What's the derivative of x squared? 2x. What's the next term? Minus 10, and then my third term becomes 0 when I differentiate. All right, denominator, what do I get for the derivative? 2x minus 2, and then I have that plus 0, which I don't have to write down. Now if I plug in 7, I'm not going to get 0 over 0. What am I going to get? 4 over 12, which reduces to 1/3. Now it said verify by using a second method. One of the things we did in Chapter 10 is we factored when we could. Look at these. These are trinomials. Is there a pair of numbers that I could get to multiply to give me a positive 21, add to give me a negative 10? Yeah, this numerator factors into x minus 7 times x minus 3 over... Let's see if the denominator factors. Is there a pair of numbers you could multiply to get negative 35, add to get negative 2? That's right. X minus 7, bless you, times x plus 2 will work. And do we have a common factor, top and bottom? We could cancel out the x minus 7s. Remember, what that tells us is we actually have a whole when x equals 7. Now, if I sub in directly, I've got 7 minus 3 over 7 plus 2, which is that, no.
That's supposed to be a 5.
Oh, you're, sorry, x plus 5, you're right. Over 7 plus 5, thank you. I'm acting like it's Monday and it's Wednesday. So that's a 4 over 12, which reduces to be 1/3. We got the same answer. So we verified it really does work. Okay, and there are more of these problems. Do you feel like you need more examples, or does L'Hopital's rule make sense? Are we good? Okay.